For years, machine learning was defined by manual feature engineering on highly structured data. That era is now completely over. The modern frontier instead relies on self-supervised learning over massive, completely unstructured datasets. To understand why this requires a new approach to system design, we have to look at the math. Traditional, discriminative models are built to draw boundaries. They classify data by learning conditional probabilities, expressed mathematically as P of y given x. Generative AI has a different objective. Instead of finding a boundary, a generative model must learn the underlying data distribution itself to synthesize entirely new instances. It has to calculate the probability of x alone, or the joint probability distribution of x and y. Legacy machine learning architectures physically fail when forced to compute these generative probabilities at a massive scale. They lack capacity to handle the parameter counts or unstructured data loads required to output a high-fidelity image or a coherent paragraph of text. Mastering generative AI requires abandoning legacy mental models. Success depends on the physical construction of an entirely different computing architecture rather than an algorithmic upgrade. When facing an open-ended system design challenge, like building an enterprise chatbot or image editor, engineers often make the mistake of immediately picking a popular model. Surviving these challenges requires replacing guesswork with a strict linear evaluation framework. This flowchart outlines the 7-step machine learning system design protocol, a progression to solve problems systematically from initial scoping to deployment. Step 1 is clarifying requirements. Here, we isolate exactly what the system does from how it performs. We divide these into 2 categories. Functional requirements define the core capability. For instance, the system takes a text prompt and generates a custom image. Non-functional requirements define execution boundaries, dictating acceptable latency, total throughput, hardware scale, and required safety guardrails. Attempting to select an algorithm before mathematically defining both sets of constraints guarantees system failure at scale. The requirements dictate the physics of the system. Step 2 is framing the problem as a specific machine learning task. This requires explicitly defining the input and output modalities. Defining whether the system is ingesting text, audio, or video, and what it needs to produce, acts as an immediate filter. It eliminates entire classes of algorithms before a single line of code is written. This taxonomy tree illustrates the primary division in machine learning architectures: discriminative versus generative tasks. A text-to-image requirement instantly pushes an architect down the image generation branch, where choices narrow to variational autoencoders, GANs, or diffusion models. Here, the non-functional requirements finalize the decision. An architect might discard VAEs or GANs in favor of a diffusion model because the specific prompt demands higher quality, even if it requires a slower generation speed. Algorithm selection in an enterprise environment is a deterministic output of strict input and output framing, not a creative engineering choice. Once selected, the architect must confront the physical hardware constraints required to run it. We habitually measure model complexity by parameter count, like 70 or 400 billion parameters, but evaluating a system's physical footprint purely by parameter count is an incomplete metric. The true currency of system architecture is the FLOP, the floating point operation. This fundamental measure of computational cost dictates the actual strain placed on the hardware. This diagram of a single output neuron tracks the weight multiplication and summation logic for a single pass. Calculating one output requires 4 multiplications and 3 additions, exactly 7 floating point operations. Architectural decisions alter this math. Dense neural layers require significantly more flops than sparse connections to execute a forward pass, even if the total parameter counts are identical. An architect's true budget is measured in flops. Hardware limitations, not theoretical capabilities, ultimately dictate the viability of the algorithm chosen. When we apply this flop calculus to modern generative models, the numbers scale sharply. Training Google's Palm 2 required 10 to the 22nd flops, pushing us into the realm of exaflops. This massive compute requirement is driven by scaling laws. empirical mathematics mapping compute budgets to performance improvements. These charts plot test loss against compute, dataset size, and parameters, revealing a predictable power law trend. But the middle graph highlights undertraining. DeepMind proved dataset size must scale linearly with model size. You can't just build a larger model, it needs proportionally more data. Executing these laws requires extreme infrastructure. The training load is distributed across thousands of specialized hardware accelerators, like GPUs or TPUs, running in parallel for weeks. Scaling is a predictable physical law. System design here is a rigorous exercise in resource allocation. This brings us to step 3, data preparation. Traditional machine learning relied on highly structured ETL pipelines. Generative AI departs from that model. This architecture diagram visualizes the modern ingestion pipeline. Massive, unstructured datasets, comprising text, images, and video, are scraped directly from the internet, accumulating into trillions of raw tokens. This specific segment of the pipeline details the mandatory cleaning heuristics. Before any token touches a model, raw internet data is forced through filtering to detect harm, remove low-quality content, deduplicate records, and scrub NSFW material. But we quickly hit a data efficiency bottleneck. What happens when the high-quality organic data required to satisfy scaling laws simply doesn't exist? This flowchart highlights an emerging solution, a synthetic data feedback loop. Existing generative models synthesize new, diverse data, which is then fed back into the collection pipeline to train the next generation of models. In generative systems, brutal data quantity and ruthless cleaning heuristics replace manual feature engineering as the primary drivers of output quality. Looking back at our complete design protocol, we have framed the algorithm, calculated the compute budget, and mapped the data pipeline. But none of this works without the underlying infrastructure layer. We have to physically move trillions of tokens into thousands of GPUs without bottlenecking the entire cluster. This requires sharding. Massive volumes of unstructured data are split into smaller fragments and distributed evenly across storage networks, allowing parallel access and preventing traffic jams. High-speed indexing technologies prevent critical I/O delays during retrieval. Simultaneously, memory optimization protocols like Meta's fully sharded data parallel reduce redundancy across devices, ensuring the GPUs spend their time computing, not waiting. Without these distributed storage and optimized memory techniques, the theoretical scaling laws collapse upon real-world execution. The final reality check occurs at deployment, where the theoretical capabilities of the model collide with production constraints. There is an inevitable tension at scale. An architect must balance the highest possible generation quality against inference latency, all while managing the cost of serving the model to millions of users simultaneously. Furthermore, the deployment must include systemic guardrails designed directly into the inference loop to mitigate security risks, from data poisoning to confident hallucinations. The machine learning architect proves that a system can safely scale data and compute within strict engineering and financial boundaries, making model code only one component of a rigorous mathematical proof.